Fantastic! We've converted our words into tokens, or Lego bricks, and given them mathematical meaning using vectors. Now we tackle the most important feature of language, order. Language isn't just a bag of words, the order matters. This is where sequence data comes in.
Sequence data, the chain of meaning. Up until now, we've talked about what a word is by itself. But what makes an LLM useful is its ability to understand an entire conversation or paragraph. This brings us to sequence data. A sequence is just an ordered chain of tokens. Everything you input to an LLM, from a simple hello to a 10-page document, is fed into the model as one long, numbered, ordered list of token vectors. The model doesn't just look at the word apple, it looks at I, then 8, then Anne, then apple. It's all about the chain.
Why order matters. The order is crucial because it changes the meaning, which is why we call language sequential data. Let's use a very clear example. The cat chased the mouse, and the mouse chased the cat. Both sentences use the exact same tokens, but the order is flipped. As humans, we know the meaning is opposite. The LLM is trained to understand this change purely through the sequence. Its main job, in the heart of its training, is called next token prediction. It constantly asks itself, given the sequence the mouse chased the, what is the most probable next token? In this case, it learns that cat is the most likely token to complete the sequence, and it will give that token a high probability score.
The context window, the LLM's memory. This concept of sequence brings up a huge limitation, the context window. Imagine the LLM is a chef with a small cutting board. It can only look at and process the ingredients, i.e. tokens, that fit on that board at one time. The context window is the maximum number of tokens an LLM can see and consider to generate the next token. Current LLMs have context windows ranging from thousands of tokens, like 4,096, up to hundreds of thousands, like 128,000. Crucial point. This is the LLM's short-term memory. If your input text, plus the ongoing conversation history, exceeds this token limit, the model forgets the oldest parts of the sequence. It's literally truncated or cut off from the beginning. The bigger the context window, the better the model is at tasks that require long-range understanding, like summarizing an entire research paper.
Positional encoding. If the entire sentence is just a long list of vectors, how does the model know which position a word is in? When we feed the sentence into the transformer, we can't just rely on the physical order of the tokens, because the attention mechanism scrambles that order. The brilliant solution is positional encoding. Think of it as giving every single token a special, unique position badge. This badge is actually another short list of numbers, a vector, that tells the model its exact spot in the sequence. For example, I am the 10th token in this sentence. We then add this position vector to the word's original embedding vector. This guarantees that the token for cat at position 2 is mathematically different from the token for cat at position 7. The model always knows the order, no matter how the data is shuffled internally. This simple concept is what allows the powerful transformer architecture to process an entire sequence all at once, while still preserving the vital meaning derived from the order.